SwayamPrabha. Digital India. Educated India.
Welcome back. So, we will continue our discussion on the hopper feeders that we started in the last class. So, we started discussing the external gate hopper feeder, and I said that here the design is quite simple, like we have a stationary plate. On the stationary plate we have a stationary outer sleeve, and within that sleeve there is a rotating inner sleeve. This rotates, and in the inner sleeve, rotating inner sleeve, we have the slots. In this section you can see this, and the mass of the parts is at the bottom of the rotary inner sleeve, and while rotating, the mass of the part, from the mass of the parts will be nested in the grooves, and when the grooves will be aligned with the external gate is on the stationary outer sleeve. So, the parts will be coming one by one through the external gate. This is the simple design of this. Okay. Now, the maximum feed rate that you are getting from this hopper feeder, that will be decided by the velocity and the distance between the adjacent slots. Okay. So, let us see how it can be determined. Now, these are the three positions of the part which is shown in the figure here. Here this is the rotary outer sleeve, rotary inner sleeve which is rotating, and this is the fixed sleeve which is stationary. Now, at a limiting velocity v, if the velocity is a certain value, then the part will neither fall to the through the gate, nor it will go through, but it will jam between the slot, between the edges B here and the C. All right. Now, at any velocity below the critical velocity v, the part will drop through the gate, because if the velocity is very high, in that case by inertia it will pass through the gate and it will not fall. At a lower velocity, it may actually clog between the B and C. At a particular velocity, which is an optimum velocity, the part will actually drop through the gate. Keeping that in mind, let us say in this figure, let us say first figure A. In this figure, the part is just started falling, it is at the edge of the gate. Now, in this figure, okay, the part has moved certain distance horizontally and certain distance vertically. All right. So, from the with respect to figure A, in the figure B, the part has moved horizontally. How we can find out that this is 1/2 root over d square minus hg square. So, we can find out from here. All right. So, this is the d by 2. So, actually the part has moved up to d by 2, okay, diameter of the gate or diameter of the part. So, this can be given by this square is equal to this square plus this square, all right, and from here we can find out that this horizontal distance, that is d by 2, this will be equal to d minus, this is d by 2, half of the root over d square minus hg square. Okay, this is d by 2. So, d minus d by 2 will be d by 2. So, this actually is moved by the horizontally moved by the part. Now, at the same time, when it has moved horizontally from this position to this position, it has also moved vertically, and that vertical distance will be d by 2 minus hg by 2. All right. Now, the horizontal movement has been done because of the v. So, that interval, that is time taken to move the part horizontally from this position to this position, will be distance divided by velocity, the velocity at which the part is falling down the gate that we are taking, and vertical distance, that is the part is falling, that is because of the gravity. So, that is why we can say that this time we can find out from the normal equation, that is L is equal to half a t square, where the t is equal to root 2 L by a. A is the gravity, L is the distance. So, this distance L here is this. So, this is the distance 2 into L, 2 into this distance divided by the acceleration. Now, in our case it is the acceleration due to gravity. So, the time that is taken for the part to fall vertically, okay, this can be given by this equation, and this time is the time at which the part has moved horizontally from this position to this position. Okay. Now, since the time is the same, meaning that at the same time the part is moving horizontally as well as vertically. So, therefore, this one we can equalize with this, all right, and we can find out that from this we are finding out that this velocity at which the part will fall through the gate will be equal to 0.802. If you solve this equation, you will find out that this is 0.802 d into g to the power half. D, by the way, this is the once again gate diameter or the part diameter, g is the gravity, and this is root over. So, this can be easily found out. To give the largest value of the velocity, the gap h g which you have here, this between the cylinder and the sleeve should be as large as possible. So, when the gap between the sleeve and the outer disc will be as large as possible, then the velocity will be maximum. Okay. For values h g greater than d by 2, however, there is a danger that the parts may become jammed between the corner B in the slot and the inner surface of the sleeve. What we mean to say is that if this distance h g, this is more, in that case this part will be jammed between B and the C or somewhere inside this within that sleeve. Taking h g is equal to d by 2, because as we said that if it is greater than d by 2 it will be jamming, if it is less than d by 2 it may not go through. So, let us take h g is equal to d by 2, h g we are saying is the gap between the inner sleeve and the outer sleeve, okay, this gap, and if this is equal to d by 2, put the h g is equal to d by 2 here, then the F maximum can be found out from the velocity divided by the A s, which is the distance between the adjacent slots, and this will be equal to 0.802 d g to the power half is the velocity divided by the distance between the gap between the slots will be A s. So, divided by the A s. In general, not all the slots will contain parts, and if E is taken to be the efficiency of the feeder, the actual feed rate is given by this into the E. That means, this will be the efficiency. If you remember, we said last time while discussing the reciprocating tube hopper feeder and the center board hopper feeder, we said that not all the time the feeder can actually provide the desired number of parts. So, therefore, there is a concept of efficiency, and the actual feed rate should be the maximum feed rate into the efficiency. So, here it, I hope this is understood. Here only please put this efficiency, because 0.802 d g to the power half by A s, this is the F maximum, and actual feed rate F, this is actually F max into the efficiency. And the efficiency, as it was discussed earlier, can be found out experimentally, that is, you are running the feeder sometimes and find out that what is the average number of parts coming out. From there you find out the efficiency, and the efficiency to be multiplied by the F maximum to get the actual feed rate, which will be of course less than F max, because F max is the ideal situation where the maximum number of parts can be delivered, but in case of the actual feed rate, since it is multiplied by the efficiency, efficiency is normally less than 100%. So, therefore, F is less than the F maximum, that is actual feed rate will be less than the maximum feed rate. Well, the next feeder, this is the rotary disc feeder. This configuration is given in the pictorial view here. Parts are carried by the slots in the rotating disc around the stationary plate until they are aligned to the delivery chute. Now, here there is a stationary hopper, and the base of the stationary hopper rotates and in the base of the stationary hopper there are slots, and those slots are protected by, as you can see, this is protected by the ledges here at the ledges. These ledges will not allow the parts to fall if they are nested in the slots, and it will also be parts will also be protected by this middle disc, which is actually stationary. So, the parts will not fall down in this direction while rotating because of this stationary disc, and because of the ledge the parts will not fall in this direction as well. So, the parts will be picked up from the base of the rotating disc, base of the bowl here, and when the slots will be aligned with the delivery chute, the parts from here will be going through the sliding down and going through the delivery chute. There are two types, one is the indexing rotary disc feeder, another is the rotary disc feeder with a continuous drive, in the sense that there are for example, the one that is shown here, that for small cylindrical parts, that means few of the parts will be nested on this slot, and therefore, when it is aligning with the getting aligned with the delivery chute, it has to stop for some times, so that all the parts could slide down the slot. Okay. Now, if it is a continuous drive, in that case it will not stop when it is aligned with the delivery chute. So, therefore, the parts have to be different. Normally, we will discuss at a later stage that those parts are the disc type parts. So, one at a time it will go. So, it is going through the delivery chute, at that time it is not stopping, but that part is falling down because there is only one part. So, there are two types, one is the indexing rotary disc feeder, which is shown here. That means, once again it will go and stop in the next position for some times for all the parts to slide down, and then it will continue rotating and so on. Now, here in the indexing rotary disc feeder, it is if a Geneva mechanism is employed to index a rotary disc feeder, the time taken for indexing will be approximately equal to the dwell period. So, this we are assuming that this is driven by a Geneva mechanism. So, when it is indexing and when it is dwelling, let us say those two times will be the same, that is the indexing time and the dwelling time till the parts are moving down the slots. The time is time Ts, let us say, required for all parts in one slot to slide into the delivery chute is given by this. This you may remember that this we have actually done that this is the acceleration, okay, and this is the length. So, we are taking, we have also discussed it earlier. So, this is the one that is the time interval, or in another one also we have shown that this is the dwell time. Okay. So, this dwell time is given by 2L divided by this acceleration, and this acceleration we found out. So, similarly, we are getting actually in this feeder also, the Ts square will be equal to 2L divided by G sin theta minus mu d and the cos theta. Now, the L, small l is the length of the slot, as it was in the case of the other feeders. We have seen that theta is the inclination of the delivery chute, and mu d is the coefficient of dynamic friction between the part and the chute. With a Geneva drive, the total period of indexing cycle Ti is therefore given by, since we said that both the time is the same. So, it will be 2 into this Ts. So, it will be 2 Ts is equal to 8L divided by G sin theta minus mu d cos theta root over, all right. So, this is the total time taken for the for this to go up and down, meaning that it will be indexing and the dwelling. If capital L is the length of the part, the maximum number that may be selected in a slot is small l divided by capital L. Small l is the length of the slot and capital L is the length of the part. This we have seen earlier. Now, in practice this does not happen, this is the maximum number of parts. So, it will be multiplied by the efficiency as it was done for other feeders, and therefore, that actual feed rate or actual F value of the F, which is the feed rate, will be given by the maximum feed rate into the E, which is the efficiency, and maximum feed rate we found out that this is the value. So, therefore, we can find out what is the mean feed rate or average feed rate. So, this is also called the mean or average feed rate, and without E, when you are not multiplying by the E, this is actually the maximum feed rate that the feeder can provide. Now, here let me tell you why this we are bothered about the maximum feed rate and the actual feed rate. See what happens, all these bowl feeders right now that we are discussing, these are all connected to the assembly machine, as I said. Now, the parts are being fed from the feeders to the assembly machine, and there has to be some kind of a feed rate that to satisfy the requirement of the assembly machine. If the feed rate is more than the machine can accept, in that case there will be a clogging, because the machine will not accept less than or more than what it requires. But if the feed rate is less than the machine can accept, in that case machine has to wait, machine has to starve, we say. Okay. So, therefore, we have to very scrupulously design the feed rate of each of these feeders, so that it can satisfy exactly the number of parts that the assembly machine requires. Okay. Therefore, this efficiency, finding out the efficiency is very important for each of these feeders. Now, there is another hopper feeder which is called the centrifugal hopper feeder. Now, in the centrifugal hopper feeder, the working process or the principle is very different. Here what happens is that there is a hopper, okay, this is the closed, and the base of the hopper rotates at a velocity, so that there is a centrifugal force and the parts are located at the base. It is little inclined. At the outer periphery of this inner wall of the hopper, there are slots, okay, as it can be seen from the figure. Now, the parts, small parts, when the hopper is rotating, the parts will start also rotate, and then the parts will get the centrifugal force, so that they will go to the outer periphery, outer wall of the hopper, and they will get nested in the subsequent slots. Now, when these slots will be aligned to the delivery chute, which is at a tangential to the wall of the hopper, the parts will be coming out. These parts will be coming out from the delivery chute. This kind of hopper feeders are suitable for feeding plain cylindrical parts, that is one thing, and the unrestricted feed rate is proportional to the square root of the hopper diameter and inversely proportional to the length of the part. This we can show later, but what is, let us see first what is unrestricted feed rate. Unrestricted feed rate is the feed rate when the hopper feeder is not connected to the machine, not connected to the assembly machine. Okay. That means, this is not related, now the feed rate is not related to the number of parts that machine requires, all right, and that is why it is called the unrestricted feed rate. Let us see how it happens. If a part is moving with constant velocity v around the inside wall of a centrifugal hopper, the radial reaction at the hopper wall is equal to the centrifugal force, and that centrifugal force is 2 mpv divided by square divided by d. So, mpv square by d, this 2 into mpv square by d is the centrifugal force at which the part will be this is the centrifugal force imparted on the part, and the part will be thrown to the outer wall inside the bowl feeder, where mp is the mass of the part and d small d is the hopper diameter. The frictional force Fw, this is the frictional force at the hopper wall, tends to resist the motion of the part, and this is given by 2 mu w mp and the v square divided by d. Okay. Now, if you see from here, well, this is understood because this is the centrifugal force. Okay. So, this centrifugal force is multiplied by the mu w, which is the coefficient of friction between the part and the hopper wall. Okay. So, if this force is multiplied by the coefficient of friction between the part and the hopper wall, this will give you the frictional force at the hopper wall which will tend to resist the motion of the part when the parts are coming towards the slots. When the peripheral velocity of the spinning disc is greater than this velocity v, the disc slips under the part, okay, and the frictional force F b between the part and the spinning disc is given by this factor. Let me explain it to you. What is it? What we are saying is that there is a part velocity v, okay, at which this is happening, this velocity in fact we are talking about, all right. This is the constant, parts are moving with a constant velocity v. Now, when the spinning disc velocity is more than this velocity, the part will slip under the spinning disc, over the spinning disc, because the spinning disc velocity will be more than the part velocity, and then there will be a force, frictional force between the part and the spinning disc, and this can be given as the mpg will be the mass of the part into the gravity, and this is the force which is acting actually when the part is on the spinning disc, and this will be multiplied by the coefficient of friction between the part and the spinning disc, which is mu b. So, similar to this, for example, if you see here, this is the force into the coefficient of friction, here also this is the mp and the g which is acting down, and this will be multiplied by the mu b, which will give you the frictional force F b between the part and the spinning disc. Now, these two F w and the F b, they are same because this is the same part and the same material that is there. Only thing is that material of the spinning disc and the material of the wall may be different. So, therefore, we are saying that this is the mu w and this is the mu b, all right. So, if we equalize them, that F b is equal to F w, and then if we solve, then we will get the value of the v, which will be equal to root over g mu b small d is the hopper diameter divided by 2 into the friction coefficient between the wall and the part and the hopper wall. This is the mu w. Okay. So, this velocity is important to find out because, as we said, that the feed rate can be determined from here. This will be F max is equal to this velocity that we found out here, this velocity divided by the L, which is the length of the part, all right. So, knowing the V, knowing the length of the part, we can find out that what will be the maximum feed rate. Well, why we are saying that knowing the velocity? Because we know the G, we will be knowing mu B, we know because we know the material, we know the material of the part, material of the spinning disc, material of the wall. So, we can find out what from the handbook what is the mu B and what is the mu W. Mu W is the frictional coefficient between wall and the part. So, if we know the material of the wall, material of the part, then you can find out mu W. Material of the spinning disc and material of the part gives you the mu B. So, these are known. We have selected the hopper diameter, okay, small d. So, all these factors will be known. Part length we will be knowing. So, therefore, we can find out exactly what is the maximum feed rate. That we can adjust. Of course, the maximum feed rate will not get, as we said, that it has to be multiplied by the efficiency, so that we could get the actual feed rate, and this actual feed rate we have to manipulate, so that it could be this is the unrestricted feed rate, as we said, that when this feeder is not connected to the machine, assembly machine, but when it is connected to the assembly machine, we can adjust this F accordingly, okay, accordingly how much the assembly machine can take. Okay. This equation shows that the unrestricted feed rate, which is F, from a centrifugal hopper is proportional to the square root of the hopper diameter, square root of the hopper diameter, and inversely proportional to the length of the part. Okay. So, this is important. When I said that we can actually manipulate, that means we can adjust this actual feed rate when the feeder is connected to the assembly machine. Since we know that this feed rate depends on the square root of the hopper diameter and the length, if we cannot change the length, we have another parameter which is the hopper diameter, and by changing the hopper diameter or by regulating the hopper diameter in a way, we can actually figure out that how much F we should get, so that the machine does not starve or it does not clog, meaning that this F should match with the number of parts that the assembly machine requires. So, the rest of the things we will discuss in the next class. Thank you.